So welcome back. In the previous lecture, we have discussed mathematical aspects which are involved in a formulation of quantum mechanics. And in particular, we built some more sort of thorough and rigorous parallelism between what is the mathematics of classical mechanics, which is basically linear algebra in 3 dimensions, and what is the mathematics, the mathematical environment of quantum mechanics, which is basically a sort of linear algebra in infinite dimension. So we, contrasted the notion of vector V with the notion of quantum state. And we saw that there were several analogies. For instance, that you can, represent a vector given a basis through the coordinates, which are nothing but the inner product of the vector with the corresponding basis element. And similarly, if you have a basis which is labeled by some index n, let's call it phi, let's phi n be the basis, and is for the moment a discrete index, and then will be made continuous in a moment. Then you can represent a state psi by projecting it onto the basis element, and the result is a set of coefficients that we call psi n. And this notation basically represents the equivalent of the standard inner product in this space. And we discussed that there are a few differences with respect to the standard inner products, because in the 3-dimensional space, we have a commutativity of any inner product. This is not true only for a basis element. It's true for any pair of vectors. But in the quantum state space, or better called the Hilbert space, we do not have an exact commutativity. It's something that resembles commutativity. And it's the following statement, that you can always flip the order in the inner product, but you have to take the complex conjugate of the results, because in general, inner product in Hilbert space are complex numbers, while the inner product that is used in classical mechanics is in the real field. Okay, so I think that was a big part of what we said last time. Today, I would like to focus a little bit more on operators and the notations for the operators. And I'd like to present this material going once again back to matrices. So suppose we have now a linear operator M acting on a vector space. And this linear operator M transforms vector V into vector W. And it does that in a linear way. We already discussed it, because this is in fact a linear vector space. That means that if I have M of lambda V plus, I don't know, psi T, this is going to be lambda MV plus psi T. That's nothing but linearity, right? Well, we don't need that at the moment. I'm just reminding you about linearity. Now, this is an abstract, meaning it's rigorous but cannot be taught to a computer, because these are not numbers. These are just abstract elements in a vector space. And as we discussed many times, if we want to transform this into something we can give a computer to crunch, we need to project this onto the basis. So let's say we take the inner product with the eth element on both sides. And this is a way to determine what is the eth component of the W vector. Right? But again, this is still abstract. So let me also project the v vector into its component. So we get EI M, and now let me say this is V J sum over J going from 1 to n of Vj Ej. Now if I if I manipulate this mathematical expression, what I get is the sum over J, Vj, and then Ei M Ej. And this is what I call the matrix element Mij. So from the expression 1, which is an abstract expression, we arrived to an expression 2, which is now an expression for the components, which is the famous matrix vector multiplication. This is numerical rather than abstract. Right, so equation 1 is general. Equation 2 is after you choose a specific basis set to represent the vector space. I assume we are all familiar with this at this point, but it's important to build this analogy because the main point that I want to make here is how you represent a matrix. And you basically represent the matrix by the following operation here. So let me just say that for each matrix, for each operator, given a particular choice of basis elements, which are represented this way, this means the set of basis elements ER1, EN, right? Given this, then we associate this a matrix Mij. And how is it built? I look at the action of the operator on each of the basis element, Ej. This will give me another vector. And this vector is projected into the ith element of the basis again. So basically what graphically it's doing, this is your basis vector. Say I have E1 and E2. What I do, I take M, I let it act upon, say, E1, and I will get this vector, which is probably M E1. And then I look at the component with respect to E2 by taking the inner product. And this particular number here is M21. And if I take the inner product of M E1 with respect to E1, this is M11. And then I do the same for E2. I look at E2. Let me draw in blue. Let's say E2 goes into this new vector. And then I take the components with respect to E2. This is M22. And the components with respect to E1. And that's M12. So that's how you build a matrix out of a linear operator. Now, in Hilbert space, things work exactly the same. Given some operator, let's call it in general O, then I want to associate something that I can sort of represent mathematically in a concrete way. And in general, this would be a differential operator, not just a matrix. It becomes a matrix when you discretize over space. And what do? I take, given a basis, so once again, now I take the basis of a Hilbert space. This time it goes from 1 to infinity because remember, the Hilbert space is infinite dimensional. At the moment, I'm considering the specific case of a discrete labeling of states. We might be willing to use a continuous labeling of states. I will go to that in a minute. But once I've done that, all I do is I take O, I let it act on some state M, and then I take the inner product with some different state M, and I call this OMN, and this is called a matrix element. So, because there is an equal sign here, also this guy here is called the matrix element. So given two states, the matrix element between two states, general states, say given psi and phi, let them be general states, I can always build psi, for instance, O phi. And this is called still a matrix element. Okay, so this is how you represent operator. And in some cases, the representation of the operator is as simple as possible. The simplest possible representation of a linear operator is a diagonal operator. And when does this happen? When the bases that I use are eigenvalues, sorry, eigenstates of the operator. So note, if my operator, if the basis that I'm using is actually such that, you know, it's actually the eigenstates of this operator. So for a notation wise, since I want to denote a basis of the operator, let me use the same letter here. Just to remind myself that I call ON the states because they are the eigenstates of the O operator. Well, then clearly when I will go and build OM, the matrix element OM, ON, well, what I get is I get ON, OM, ON. And if this is a complete orthonormal basis, and normally we will deal with the case in which it is, I will come to the moment to define the condition under which the eigenstates of an operator form a complete orthonormal basis. But if this is a complete orthonormal basis, remember this object will hold 1 when n is equal to m, or 0 when n is not equal to m. This is called the Kronecker delta on m, and therefore this will be delta n m o n. And if I look at this as a matrix, this means that if I have, you know, infinitely many lines here and here, I only get elements in the diagonal. So whenever you use as a basis of your vector space the eigenstates of some operator, that operator, when represented in that basis, is diagonal. So let's give an example that is quite important. Let's look at the X operator, the operator that defines the position. Now, the X operator, if you're, you know, you can consider the X operator in a crystal, then of course the positions are really discretized because a crystal, and then in that case you have like Xi, because you have a discrete number of possible positions. So you have atoms in a crystal, can be in electrons in a crystal, can be in any of the atoms. In a chunk of wire, for instance, you have a, you know, metallic wire. It means that there's a crystal underneath, and the electron can go from one atom to the other. Or you can have a continuum, and then this Xi becomes a continuous index. But let's do things gradually, and let's assume that we are in a crystal for a moment. Then clearly this is the eigenvalue times the corresponding eigenstates. Then clearly, what is the representation of this operator in this space? I have to take xj, x, xi, and this will be xi, xj, xi. Now, if these are points in a continuous lattice, of course, this is going to be in a discrete lattice or in a crystal, which basically is a discrete lattice, physical discrete lattice. And that's clearly delta Ji. So clearly, the position operator is diagonal in position space. And that's why when we were writing, oh, and any function, and so I can define our new operator, U. Sorry. Let's suppose we have a classical function U of x, which defines some potential energy. And let's assume this function is analytic. What do we mean by analytic? Well, I will not go into the proper mathematical formulation. But for me, in this course, analytic means that I can approximate this function with a Taylor expansion to give an order. I assume you're all familiar with the Taylor expansion, which means it's an expansion in derivative around a point. So given a point x naught, I'm working here in one dimension for simplicity. That's the first order. Then you have a second order. And then you can continue to all orders. Now, what happens if you do that? Suppose my U of x is like, I don't know, I'm going to draw it around the point x naught, like something like this. Let's not be too, something like this. This is an analytic function, then this is the first order. This is the second order, to say, okay, let's choose a slightly different point to avoid falling into a specific. So let's say this is my x naught. So this is the U naught. This is the first correction. This is the second correction, maybe. And then if you keep on going with the series, you become more and more local. Eventually, if you put enough terms in the Taylor expansion, you can approximate the function with a desired accuracy for as large as you want. That's the notion of analytic function. Why am I bringing out the idea that U must be an analytic function? Because if it's an analytic function, it's represented by a series of U nth derivative over n factorial. If you, these are the coefficients of the Taylor expansion. And that's x to the n or x minus x naught. Let's say x naught is the origin, x to the n. Now, this means that if I want to look at a corresponding operator, I can use the position operator to represent it. And then do the sum. So in other words, it means that if the position, if I'm using a representation, if I now go to, say, a quantum operator from this function, I build a corresponding quantum operator. This is the nth derivative in some points. This is the factorial. And now this is the corresponding nth power of the position operator. And that means that in this case, since this guy is diagonal in position representation, also this guy is diagonal in position representation. So all I'm saying is, with this long mathematical digression, all I'm saying is the matrix elements of the potential look like exactly like the position. So any function of position is diagonal in position representation. However, there are operators that are not diagonal in position representation. For instance, the momentum operator we already discussed, right? Momentum operator in position representation, they're not diagonal. But this is not simply a pi xi. And in fact, we can discuss that this is in fact basically a derivative in position representation. Okay, And we have seen that already in the previous lectures. So that's how you represent operator. So we know how to represent states, and we have to represent operator. Now, throughout the discussion, I made the assumptions that the operators have a complete orthonormal set of eigenstates. But, of course, from our experience in matrices, we know that this is not always the case. So the question that we want to address is, under question, under what conditions some operator UO has a complete and orthonormal set of eigenstates. Now, when you address this problem with matrices in real vector space, a theorem tells you that if you have an orthogonal, basically a symmetric matrix, not an orthogonal, symmetric matrix, then you have a complete set of states and the eigenvalues are real. So now we might ask the same question, under which, since you have this both these properties together for symmetric matrices in real vector spaces, maybe they come together also in complex vector spaces. So let me ask a second question. Under what condition the corresponding eigenvalues are real, even if the matrix is not real. Now, so I now have two questions. It turns out that both such questions can be answered at once by a single theorem. Let's call this theorem Jordan, and for historical reason it's called lemma. Jordan was a mathematician who was also involved in the development of mathematical formalism of quantum mechanics. So basically, what this theorem says is the following. I'm twisting a little bit the notation here. So let's for a moment use a slightly different notation to make clear what I mean. So far we've used the notation to denote inner product. Let me for a moment use an equivalent notation which is often used in mathematics. So this would be like EI dot EJ equals EI, comma, EJ. You might have seen this notation already in your crash test on linear algebra. And I want to use this because this notation makes things slightly more explicit. And you find it more often when you discuss hermiticity than the Dirac bracket notation. So if you go in book and discuss these properties, you're more likely to find this notation than this, because this is only used in quantum mechanics. This is all, by the second one is used basically everywhere you need Hilbert spaces on vector spaces in mathematical literature. So let's define the Hermitian conjugate. In Hermitian conjugation. So let's consider some operator O, generic. Then I can always take two vectors and take, so I'm mixing the notations here. Let O act on phi, and then take the inner product with psi. This is basically what we were doing to build the matrix element operation, right? You get the operator acting on the first vector, and then you take the inner product for the second vector. Now, I define another operator, O dagger, such as that operator, for which if I let the second act on the left and take the inner product with phi, I get the same results. So in general, O and O dagger, O is not equal to O dagger. Let me give you an example of a non-Hermitian operator. Okay, so I said a sentence that you probably do not have the background yet to understand. I said, let me give an example of a non-Hermitian operator. I didn't tell you what an Hermitian operator is. I'm saying, in general, these two operators, the one that acts on the right of the comma and the one that acts on the left, and is defined in terms to be the one that gives you the same result as the previous one acting on the right. So this is a definition. In general, these two operators are not the same operator. But if I happen to be the same operator, then O is Hermitian. Okay, that's the property. I mean, and if you think about it a little bit, you immediately discover that hermiticity is basically the natural extension of the concept of symmetric matrix elements to complex plane. And I will come to that in a minute. But let's make some examples. So let's take let's say psi, let's take a vectors. So let's say in coordinate representation, I can associate two states, two wave functions, phi of x and psi of x. How come? Because I've mapped state phi. I expand onto the basis of positions, for instance, and then I take the inner product of positions with my state phi, right? This inner product, which we can also represent with this second notation we just introduced, is the projection of the state phi on position representation. Is called the wave function, right? So if now I take a continuous set of position, not just a discrete set of position, the sum becomes an integral, and I can write dx phi of x, x. And this is the wave function. The representation of quantum state in position representation. Now, just as much as you can go from abstract vectors in a product to concrete way of computing in a product after you project it on position, the same way you can go from abstract inner spaces to concrete ways of computing vector spaces in inner products, right? So what does it mean? So let's consider a sum operator O. Then I can do phi O psi, and after I represent phi and psi, this is basically integral over dx, phi star of x, and then O acting on psi of x. And I put a comma to remind me that this was on the right. Let's take an example. Let's say O is the derivative. Then phi derivative psi is nothing but integral phi star x d by dx psi of x. Conversely, so the question we would like to ask here is this operator Hermitian? Now, a way to prove that it is Hermitian, remember, if it is Hermitian, O dagger is equal to O, meaning if it is Hermitian, then clearly, if O is Hermitian, O psi is equal to psi O. If it is Hermitian. In general, this is not true for non-Hermitian operator. So this is true only if O dagger is equal to O. So if you want to prove, if you want to answer the question whether this is an Hermitian operator, all you have to do is to confront this result with, compare this result in which the derivative is on the right with another result in which the derivative is on the left. So let's look. This would be d by dx of phi star of x, and then psi of x. Now the question is, are they the same? And actually the answer is no, because I can use integration by part and use the integration by part. I can switch the derivative from here to here, but I have to change sign. And I forget about the boundary value terms because the wave function assumed to go to 0 at infinity, remember? So what I get is negative psi star psi of x. Sorry, negative psi star derivative of psi of x. So this is not an Hermitian operator, because if I let it act on the left, it is not the same as if I have it act on the right. Okay? So not an Hermitian operator. However, you can immediately convince yourself that this operator is actually Hermitian. And how do I know? Well, simple. Integral dx psi of x star I d dx phi of x. And now I compare this with integral dx I d by dx psi star phi of x. Now you see what happens when I pull off the I get a negative I integral dx psi by dx phi. And now when I use integration by part, I get an extra negative sign, like before, and therefore I can pull it back and get the right result. So this operator here is Hermitian, and this should come with no surprise, because if you remember, we define an operator basically that had the structure. There was the momentum operator, which was minus I h bar d by dx for one dimension. That's dx if you want. So along the x component, this was d by dx. Along the y component, kinetic h by d by dy, and so on and so forth. The gradient in general. Now, why bothering about the emission operator? Because they don't, the Jordan lemma, states an important point. If O is Hermitian, then there will be a complete set. It has a complete set. It has, so the eigenvalues, the eigenstates, then the eigenstates of O phi n, O n, phi n form a complete orthonormal set of basis set of the Hilbert space, and two, the corresponding eigenvalues, or if you want the spectrum, is real. So ON are real numbers. So this is the mathematical theorem we really need. Basically, what this is telling us is in quantum mechanics, there is only one kind of operators we are really interested in general, with a very, 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 very limited number of exceptions. And these are the emission operators. We basically are only interested in emission operators. So this explains why the Dirac notation is slightly different from the standard notation. So remember, in the standard operator or notation that you use in mathematics, an Hermitian operator would be represented by this property. Oops. This is the standard notation. But since in quantum mechanics, we are only interested in Hermitian operators, the notation that Dirac, famous Nobel Prize winner, one of the most celebrated physicists of all time, invented, is a notation in which the operator sticks in the middle, simply because if it's in the middle, it's symmetrically applied on the right and on the left. This nice notation, which only holds for emission operators, but in quantum mechanics, basically, we only are interested in emission operators. Now, these notations it leverages on the fact that we don't care whether O acts on the right or on the left, because O will be always an emission operator. So that's why in quantum mechanics, you define this to be the matrix element between psi and phi. So summarizing all this, we have understood that in quantum mechanics, states, the state of the system is associated with points in a Hilbert space. Actually, not exactly points, because you see, well, I'll come to that. Let's say for the moment there are points in a vector space, and observable quantities such as position, momentum, or function of position and momentum, and more type of observable will come later, such as the electric charge or the magnetic moments. There are many things you can observe of a quantum system, right? But anything that is observable, So observables in general will be represented with or Hermitian operators. So that's all you need, right? So what do you need? You need something to define the state of the system. You need something to define the evolution of the state of the system. And then you need something to compute outcome of predictions given the evolution of the system, given the state of the system. And that would basically form what all is quantum mechanics. So let's sort of understand, I have an equation that tells me how quantum states evolves in time. That's the Schrodinger equation. This will give me the dynamics of the state. And this is equivalent to the Newton's equation, the given state, or the Hamilton's equation. The given state PQ of a classical system will give me the state at a later time, right? And then in classical mechanics, once I have a position, I can measure it. There's no need to go from the state to the observable, because if I know that my state is in a physical system is in a state which has a given position and momentum, I know that I can measure that position and that momentum. But in quantum mechanics, I have uncertainty principle, and the concept of what can be measured and the outcome of measurements is actually fuzzy or fuzzier than in classical mechanics. So I need to introduce an operator to define observable quantities. So the question that you are left to addressing is, how do we predict the outcome of an experiment given aiming to measure a given observable O. So let me say it again. Now we know that for each observable quantity, we must associate an emission operator. But an emission operator is not a number. So we still miss a logical step. How, given that emission operator, we make prediction, given the state and the emission operator we want to compute. So how to make prediction? Okay? Now, with everything that we said, we should be more or less in a condition to answer this question. But I want to get there sort of stepwise. And the first step is, let's take a simple cases. Let's go there. Let's answer this question, how you make prediction by examples. And then we'll generalize into a rule. And then next lecture will be devoted to listing all the rules of quantum mechanics in a tidy order. Okay, so let's take the simplest operator we have, X. And let's take my state psi. I know the system is some state psi. For instance, the ground state of the harmonic oscillator. And now let's be maybe a little bit more complicated. I take X to some power, N. So I can build any Taylor expansion, because if I know how to compute the nth power of X expectation values, then I know I can the expectation value of any potential energy, because I can expand potential energy in Taylor series. What I'm saying is that any potential energy can be written as a stiff coefficient. This is the Taylor series expansion. I'm assuming you are familiar with the Taylor expansion. If you're not, we need an extra lecture on the Taylor expansion. I hope you have seen that already in the past. Okay, so that's our example. How do we predict the outcome of an experiment that wants to measure the operator observable x to the n. We want to measure it, and knowing that the system is in state x, psi. Well, if you think about it, you would say from psi, I project on position basis, and I get the wave function psi. And from the wave function psi, I know that the modulo square of the wave function is actually the probability of observing the system at x. And therefore, if I want, what I know is that anytime I measure the system, I will find it in a different position. So anytime I will perform a measurement on my system, I will find a different values of this. So the outcome of the experiment measuring x to the n will not always be the same. Classically, because the particle is moving, but quantum mechanically, because the wave function is giving you a finite distribution of probability. The wave function will give me a distribution p of x, which maybe is something like this. So I have regions where it's the probability of finding the system is larger, and region where the probability is smaller. And anytime I make a measurement, with some probability I find the particle here, and therefore we get xn corresponding to this value of x. And occasionally I will get it here, and I will get this x prime n squared. Okay, so you know, all I can say is, for instance, I'm interested in the average value of these measurements. The average outcome of the measurement. Measurement of xn. This is also called the expectation value. The most probable, or the average more than the most probable to be actually rigorous. So on average, what comes out if I measure many, many times these observables? Well, you know, all I have to do is to take xn and the corresponding probability, which is basically xn psi star x psi of x. And I can also rewrite it as psi star x xn psi of x. So in Dirac notation, what I discovered, what I discovered is that the expectation of this operator, expectation value, can be written in the following way. So given this type psi, I can tell you what is the typical average value of all the measurements that I make by taking the psi state and sticking the operator in the middle. Since the operator is emission, any type, you know, this expectation will be real because it's a matrix element. So the real emission operator will be real. And that corresponds to the expectation value of x. Now, this rule generalizes to all operators, even those that are not diagonal in that representation. So in particular, p to the n will be taken by psi, p to the n psi. And so in general, all operators, the expectation values of all operators will be built by taking the matrix elements of the operator with its state. So let's be a little bit clear here. So let's suppose the system is a state psi, which corresponds to a wave function psi of x, and let's compute the expectation value of the momentum operator. Well, this would be negative IH bar psi, and the momentum operator, well, in position representation would be d of x psi star of x d by dx psi of x. What about the kinetic energy operator? Oops, kinetic energy operator. Well, I can obviously pull off the 1 over m squared. I know how to represent in position representation the kinetic energy is the h bar square Laplacian. So let me pull off the h bar square negative, and I get a Laplacian here. Notice that this is an admission operator because now the I has disappeared. However, in order to pull this double differential operator from here to here, I have to use the integration by part twice, and therefore I flip the sign twice. And so this is nice and well-defined. So we learned something very important. The expectation values of observable quantities are computed taking the bra of the state, the operator in the middle, and the ket of the state. And the operators will always be Hermitian, so the hermiticity guarantees to that making use of this nice symmetric notation is a meaningful thing to do. I want to make two important comments before I close the lecture. The first one is, we said that the outcome of an operator is not always the same. Like if I measure the position of a particle that has a spread wave function, sometimes I find a particle here, sometimes a particle in some other position. And so I don't always find the system in the same position. However, there are exceptions. So note that if the system is in a state that is not just any state, is an eigenstate of my operator, O, is one of the eigenstates. So what happens when I look at the expectation value of O? Well, I can do that. It's like ON, O, ON, right? I just learned that. But now this is an eigenstate of this, and this will be the corresponding eigenvalue, ON, the state, bracketed into itself. But since this is a complete orthonormal state, this is 1, and I get ON. Well, what I'm learning here is, well, if my state is in some eigenstates of the operator, anytime I measure that operator, the average value of the measurement will be the corresponding eigenvalue. We know that because if you say the system is in the ground state of the Hamiltonian, of the harmonic oscillator, then when I measure the energy, I will find the corresponding eigenenergy, right? Remember, when we have the system is in the ground state, has energy E naught, anytime we measure the energy, we'll find E naught. But this is different, right, from the position, because in the position, anytime we measured, we were finding different answers. But now I'm telling you that anytime I measure some operator O, knowing that the system is in an eigenstate of that operator, I always find the same answer. So really the question is, how do I compute, how do I estimate the distribution of outcome of experiments? So how do I understand if I'm in a situation which, this is the outcome of an experiment with a corresponding probability. Sometimes I get these values, and most of the time I get the values around here. How do I distinguish this scenario, which is the one that we, considered for positional measurements in a ground state of a, say, harmonic oscillator? How do we distinguish this for a situation that anytime I measure something, I find always the same value? Say, about. And obviously, a way to do is to estimate the width of this distribution. Right? Because if the width of the distribution of measurement is 0, then anytime you make a measurement, you find always the same value, the center of the distribution. Now, if the system is in an eigenstate of my operator, the width of the distribution of outcomes of measurements is 0. Let me denote this to distinguish from O. How do I know? Well, look, take the first, distributions at a moment. If all moments are 0, this distribution is 1 point, right? So what is the first moment of the distribution? Say, I take this divided by this. This is called, if you think about it, this is the standard deviation, right? The standard deviation tells me it's the first estimate of how width is the distribution. If the distribution is a Gaussian, is all there is. If the distribution is not a Gaussian, you might have to consider higher powers here of O and get higher moments, and all of them has to be 0 for the distribution to be completely concentrated on a point, right? But let's take this for a moment, and let's evaluate it in the case in which the system is in an eigenstate of O. So this will be ON, O square, ON, and then I will have ON, ON square. So this will be ON square, ON, ON, and this will be ON, ON, ON square. Now this is going to be 1, this is going to be 1, and all I'm telling you is ON square is equal minus ON square equal 0. So what did we get? We arrived to the conclusion that if my state psi is actually not any state, but is actually in particular an eigenstate of some operator O, anytime we measure O in the state psi, the outcome is the eigenvalues ON, defined as O, ON, ON, ON. So clearly, if the state psi is not an eigenvalue of X, so let me give you a counterexample. Let's assume this is not an eigenvalue of the position operator. How do I know? Because you see, it's a linear combination of position eigenstates, not just one position eigenstate. There's a linear combination of position eigenstates. Then when I measure X in my system, I find different values every time. However, if this is only one state, say the system is in a particular position X bar there, well, anytime I measure O, I will find always X bar. Always. So there are two distinct behaviors. If you want, depending on the operators, there are special states of the system where measurements are trivial. They always give the same result. And in general, measurements are not trivial. The result of the experiments will be distributed. So to conclude this lecture, to every observable quantity, we must associate Hermitian operator. And we have devised a rule to go from this Hermitian operator to predicting the outcome of the experiment. In general, we can only predict average values of that observable, the average over many independent measurements of that quantity. But in special cases in which the state of the system is one eigenstate of that operator, then the outcome will be consistently always the same, the corresponding eigenvalue. And we have seen that when we were already assuming that if my system is in the ground state of the harmonic oscillator, anytime I measure the energy, I find the energy of the ground state of the harmonic oscillator. I don't find a distribution of energy. But anytime I measure the position in the ground state of the harmonic oscillator, I will find a different result, and I can only compute the average value. Now, I'd like to close this lecture. I want to stretch this lecture a little longer because I want next lecture to be devoted only to summing up, and I don't want to spend one more time on mathematics next lecture. So bear with me for another 5 minutes or so. Now I'm gonna state a theorem. And I'm gonna state it without proof. I mean, in some course, I remember I was trying to give a proof, but I never asked this proof in the exam. So let's not even pretend we want to have the proof. Let's just assume it, okay? Somebody proved it for us. So consider there are two operators, A and B. And of course, they are both Hermitian. Because remember, in quantum mechanics, we are only interested in Hermitian operator. So let's consider an object called the commutator between A and B. What is the commutator? Well, it's an operator itself that you can construct out of the operator A and the operator B. And how do you construct this operator? Well, first you let A and B act in this order. First the one on the right and then on the left. And then you take the opposite order with a different sign. Now, since this is an operator, this is a product of two operators, it is still an operator. And the difference between two operators is still an operator, so this is an operator. And you can show that if this is Hermitian, then also this is Hermitian. Now, if this operator will, when acting on any function of the Hilbert space, any state, will give me 0, this means that it doesn't matter whether I first act on B on my state and then on A, or if I first act on A and then B. In this case, you say that A and B commute, right? Or are commuting operators. Now, this is a definition, not yet the theorem. So consider two states and consider the commutator. Now, if given two Hermitian operator, given their commutation, so assuming that they have a 0 commutation, so it doesn't matter which one acts first, then A and B have the same set of orthogonal, or if you want without need, same set of eigenstates, eigenstates. So in general, every emission operator has a complete set of eigenstates. And the question this theorem addresses is, under what condition two different operators have the same set of eigenstates? I'm going to draw it as a picture. A, in general, A has its own state, say AN, and B has its own state, BN, and in general, they're different. However, if A and B commute, then there is a unique state, let me call it psi n, so that when I do A psi n, I get AN psi n. And when I do B on the same state psi n, I get BN psi n. So whenever I have a commuting operator, I'll get the same set of states. Now, exercise for you, which I will discuss on Thursday, on the discussion lecture, the live lecture on Wednesday. Exercise. Show that P and X do not commute. And compute the value on the right-hand side. Because you see, there's something that relates to operators that commute to the uncertainty principle. We know that I can never measure P and X at the same time, right? With infinite accuracy. And we sort of mumble that the act of measuring P destroys the information of measuring X. Just as much as the actor measuring the Y component of some magnetic moment destroys the previous information on the X component. And you can sort of see this because you see, suppose I have some state X and I do P and X. Well, when I act X, and then I want to measure X, the expectation value of this. Now, since the system is in the eigenstates position, clearly the expectation value of this, well, let's suppose this is a discrete lattice, not to worry with mathematical details, this will be x bar. Anytime I measure, the system is in the eigenstate of position, anytime I measure, I find that position. Fine. But now suppose I first measure position, and then I measure momentum. Well, since this is an eigenstate of this would be P X times X, because this is the eigenvalue. But now this is distributed because P is not diagonal in X position. So anytime I have a non-commuting set of operator, I get a distribution of values. The act of measuring P destroys the information that I had that the system was in X and delocalizes the information on X. In contrast, let's take two simple commuting operators, X and an X squared. These are commuting. Why? Well, clearly because you know, this would be X squared X minus X x squared, this is x cubed minus x cubed, this is 0. And see what happens. I have an eigenstate of x. I measure first x and then x squared. And this will be always x. And if I take the first moment of this, the standard deviation, it will be 0. So whenever I have two commuting operator, the act of measuring the second operator, say, doesn't destroy the information gotten from the first one. Whenever I have two non-commuting operator, I'm in this uncertainty condition. So the outcome, and that's the last sentence I'm going to close my lecture with today, is a general form of uncertainty principle if A and B do not commute, okay, it is impossible to know simultaneously the state, the value of B and A with infinite accuracy. So the position momentum was a special case of uncertainty principle. Anytime I have two commuting operator, I can measure them in any order I want, and if my initial state is an eigenstates of the two commuting operators, I will always find consistently the same results anytime I make an experiment. But if the two operators are non-commuting, anytime I do this, I get a different result. Now, I'll come back to this point next lecture when I summarize all the rules of quantum mechanics. But it was important for today to